let's look at the first few spherical harmonics. Okay. And at some point, I will show you pictures, maybe even today. So I'm going to divide them into groups. The first one is L is 0, and then M has to be 0, right? So I'm not going to write the theta phi dependence. They are implied, and that's going to be equal to, it actually turns out to be a constant. And its L angular momentum value is 0. Right? Number 2 is the L value is 1, then the Ym value can be +1 or -1, and that's going to be -1 plus 1, minus plus 3 by 8 pi square root sine theta e to the power plus minus I of phi, and then y1, 0, which is also part of the multiplet. It's going to be 3 by 4 pi square root cosine of theta. Of course, because M is 0, it doesn't have a phi dependence. So they form a triplet, right? Number 3 is, so this is kind of the language, a set of 3 states which form a representation of the rotation group is called a triplet. And then if y is 2, then the M value can be a lot of things. Let's take plus minus 2. It's 15 by 32 pi half sine squared theta e to the power plus minus 2 I phi, and then y2, it can be plus minus 1. You guys are following why all these values have the values that they do, right?
Yes, barely.
L and M.
Yes.
Barely, did you say?
Yeah, somehow I'm coping up with this. There's a lot of numbers and stuff, so.
Well, you don't have to pay attention to this 15, 8 pi. These are just things that pop out of the formula, right? We don't care about those things, right? I'm just showing you how the complication grows as we go up in angular momentum. Okay.
Yeah.
So this is the last one. So and of course it's not going to have a phi dependence, right? Okay. So this is a set of 5 states. I don't know what, quintet or something. And then in general, the spherical harmonics are given by y Lm. So this is a more general formula. The constant is 2L plus 1 times L minus M factorial, L plus M factorial. If you were to memorize one formula, it should be this, 4 pi, and the whole thing is square rooted, and then we have minus 1 to the power M, e to the power I M of phi, PL cosine of theta, and and to the power M, and I think it's to the power M. I don't think it's a different. Quantum number, but let me check. Okay, I'll come back to you. Now, these PLM, they are called the Associated Legendre polynomials. Okay. I used to have a friend, a German mathematician, and she was the world expert on Legendre polynomials. She did her PhD on a generalization of Legendre polynomials. Okay, so, and here, m is between L and 0. Okay, so you might say, okay, then what is the negative value? Because m can definitely take negative values. The negative, for negative values of L, m, we define, or we can show that that's related to, that's given by the positive value of m by this formula. Okay. This is also a parity because, if I look at angular momentum states, we know from uncertainty relationship, well, they have something like this, right? The z components are defined on these cones because, what we are saying is that on this upper cone, we have positive value of m, and on this lower cone, we have negative values of m. So this is also saying that we are actually doing a parity. We are doing an antipodal projection. So this, these points are going to its antipodal points. And it's given by this. And the other thing is that P of L, 0 cosine of theta, is known as PL of cosine of theta. And these are the Legendre polynomials. When we were students at Dhaka University, we used to call them legender, as you can imagine. We didn't know that, we didn't know French, so we still don't, but we have now pretensions of knowing French. Okay, any questions? So a lot of it is just like information I'm giving out, right? But at least, the story should be clear. The story is that, okay, let me just make some concluding remarks, is that, when we have a spherical symmetric system, a spherically, symmetric system, its wave function psi, which has quantum numbers of energy L and m, naturally divides into two factors. One is a radial wave function. And in next lecture, we'll see that its quantum numbers are the energy and the total angular momentum. And then a angular part, which is YLM, and it's called the spherical harmonics. And these guys, we can find them by solving the eigenvalue equation of Lz. YLM is mh bar YLM, and and then L plus acting on YLL0, and from there, we just find all the others by applying the lowering operator on YLL. Okay. And and that's it. This is conceptually very easy. Mathematically, it's a bit involved, but conceptually, this is not very hard to understand. Okay. So, any questions about the storyline or even details?
I don't think I have any. Everything seems to be all right. Well, it's simple, but also it's very involving. Okay.
It's very involving, exactly. Conceptually, it's very simple. Conceptually, we have been dealing with angular momentum since the beginning of this course, essentially. Except for the first few lectures, all we have done is angular momentum, right? So it's
the background really helped out.
Yeah. So all those things are coming to fruition here, right? So next, next lecture, we will deal with the radial equation. And that's where, different systems will have different behaviors. Okay? All right, any more questions? Okay, if not, thank you very much. And sorry for the regular timing. I will try my best. We will, we'll have the regular time on Wednesday.
Thank you, sir.
Okay, thank you very much.
Okay, thank you, sir. Goodbye.